let's now talk about how do you solve this problem. So there's a couple of ways you could think about solving this. One might be to use a cryptographic hash function. So if I jump back to this, we would just solve it by hitting this part here. Create a hash table, or sorry, a hash function that's not easy to reverse engineer. And that's because it's infeasible to create a pathological data set for this function. So if you look at a function and you have access to it, it's open source, it's a cryptographic hash function, that doesn't mean that it's easy to figure out how to make it have all of the items mapped to the same bucket. You still probably have to, at that point, to do a brute force search where you generate a bunch of items and see, okay, these are all the items that map to bucket X. So let me just hold on to those and call that my pathological data set. But that's still sort of prohibitively hard. So it's not theoretically impossible, but it's difficult. And if at any point in time, somebody decides, well, they found a way to crack that hash function, which has happened, crack that cryptographic mathematical equation, essentially, then now all of the hash tables implemented with that have to be updated. So a much better way around this problem is to go low tech. So we're still going to have something here that's an open source implementation. It can be publicly viewed by everybody, but it's going to use some randomization. So instead of having a single hash function, we're going to have a family of hash functions. And then at runtime, we're going to randomly pick one. So let's say I have 400 hash functions in here. Hash function 1, hash function 2, hash function 3, all the way up to hash function, 400, if that's what I just said. Well, okay, so somebody might be able to crack all of those hash functions, but how do they decide which one you're using at runtime? If you randomly select one and the hacker has no idea the process by which you select it, maybe it's dependent upon the time of day that you start the process, maybe it's dependent upon the current temperature outside, there's no way for a hacker to figure out which one of these hash functions you're using, so they don't know which pathological data set to attack you with. Well, if you only have 400, maybe they can just try all 400 pathological data sets and see which one hits the mark. So instead of your family of possible hash functions only being 400, typically you're looking at like billions. Is that billion? Yeah, sure. So effectively, you make it impossible for them to tell which hash function you're using. Well, how do you come up with this many hash functions? Let me give you one example, and this is a pretty straightforward process, surprisingly. So let's pick a particular problem just to make this more concrete. And let's say that, again, we have a set of hash functions. Okay, so now it's not a lowercase h, it's an uppercase h to say we have a set of hash functions. And they're still going to map from the universe, and every single one of them is going to map from the universe into this domain of 0 to n-1, our buckets, our hash table buckets. Well, we can say that this hash family, this hash function family, is universal. So this is where the idea of universal comes from, and meaning it's good. It can't easily be hacked as a way to think about universal. If and only if for all x and y of the universe, so we're going to pluck out any two x and y values from the universe, what we're going to find is that the hash family is universal if the probability for any given hash function of x and y having the same hash value if it's less than 1 in n. So that's the probability of a collision. And we're going to say that for any h, that's uniformly chosen at random from h. So lowercase h from the family h. So that's a little cryptic to try to understand. So another way to think of this is the hash functions don't all have the same flaw where they map the same set of inputs to the same bucket. So if all my hash functions have a collision between x and y, and that could be for any x and any y, they all sort of have that same characteristic, well then we don't really have to care about which hash function from the family that you're using. We just know that our pathological data set in general is going to work no matter which hash function you use. So this property is actually not too hard to show. It's actually not too hard to come up with hash families that exhibit this universality property. Okay, so let's go through a concrete example. Let's say we're working with IP addresses. What is the universe? The universe is simply all possible IP addresses. So if you're not familiar with an IP address, it's really just 4 numbers, x1, x2, x3, and x4, where each one of those values is from the range 0 to 255. So you've probably seen something like 192.0.19.0. So that's an IP address. I don't know if that particular one I just wrote out is a valid IP address, but that's an IP address. So the next question would be, how many IP addresses are there? So how big is the universe? Well, how many different values can we have for the first IP address? There are 256 values, so 0 through 255 inclusive, and then 256 for the second second value, 256 for the third, and 256 for the fourth. So that means that it's 256 to the 4th power total number of IP addresses, which is 4 billion. So this is for IPv4, which if you've heard of IPv4 versus IPv6, this is part of the problem with IPv4 is we don't have enough IP addresses. When everybody has a laptop, a phone, and 16 appliances in their home that all are presumably needing an IP address, maybe those are on the local network though, maybe those don't need a public IP address. Point is, it's not as many as you might think in terms of universe. Still, large enough universe that we don't want to have a single bucket for every possible IP address in our code. Okay, well let's say that we want to store some number of objects, and let's say we want to store 500 IP addresses. So let's just pick 997 as the number of buckets. So here's a semi-proper value for n. It's a prime number. It is a little close to a power of 10, but we're going to work with it here. So what could be our hash family? Let me describe one possible hash family. It's going to be every hash function defined by this equation here. So it's a.x mod n. So where do we get our family of functions? Well, we're going to choose at runtime these values for a. So if you're not familiar with the dot product, that's what I mean by a.x here. If you're not familiar with the dot product, this is essentially all it is. You're going to take a1 times x1, a2 times x2, a3 times x3, a4 times x4, and then add all those numbers together. And then we still have to mod by n to make sure that we're not indexing outside of our bucket. So why is this a hash family? Well, we could pick any values we want to for a1, a2, a3, and a4. Just for the sake of this argument, let's restrict the range for our values of a to the range 0 to n minus 1. So that means that our hash family includes all combinations of the coefficients in a. So my next question is, how many different possible hash functions are there? So how big is the hash family? Well, similar to how we had 256 to the 4th up here, for this we'll have n to the 4th, where n is 997, which is 988 billion possible hash functions. And if we exhibit this trait of the family being universal, that means that our hacker would have to come up with 988 billion different pathological data sets and then get lucky and figure out which one of those mapped to the current hash function.